this page was. Let's do some applications, and there'll be applications where the algebra itself will be really quite easy. Some of the algebra on that first page got kind of complicated, right? I mean, not terrible, but complicated. Let's do ones where we'll solve actual problems that are based on reality. Let's talk about radioactive decay. So radioactive substances have the property that their rate of decay is proportional to how much of that radioactive substance there is. In some sense, it's like each individual radioactive particle has some probability of decaying at any given moment. So that proportion of that material will decay at any given moment. As a consequence, no matter how much of a radioactive material you have, it will always take the same amount of time for half of that material to decay. That amount of time is called the half-life, often denoted lambda. And once you measure the half-life of a substance, you can express the quantity at any given time by just figuring out how many times you need to divide by 2. Right? If you know that 5 half-lives have passed, you know that you should divide that quantity by 2 5 times, so 2 to the 5th. But what does it mean that, how do you figure out how many half-lives have gone by? Well, that's just division. If 10 years have gone by and the half-life is 2, then 5 half-lives have gone by, because that's 10 divided by 5. So if you unpackage that a little bit, you'll see that if you have a substance that's decaying radioactively, then the quantity at any given time will be given by the initial quantity times 2 to the negative, figure out how many times you have to divide by 2. That'll be 2 to the negative t divided by the half-life, because, well, t divided by half-life is the number of half-lives that have passed. People feel okay about that? I mean, in some sense, it's just a formula, and we're just going to use that formula. But that's the motivation for where it comes from, how you can think it through. So let's do an application. So here's a particular half-life, uranium-232, U-232. That has a half-life of 70 years, approximately. I think it's close to like 67 and some change years. But I want to make the numbers as pleasant as possible to work with, especially since I don't really care about the answer. And I'm going to forget this answer as soon as I'm done this problem. So if U-232 has a half-life of 70 years, and you have a sample of 1 kilogram of U-232, let's think about how long it'll take that 1 kilogram of U-232 to decay down to 1 gram worth of U-232. That seems like a reasonable goal. Let's write down these quantities. So I know that the quantity at any given time is equal to the initial quantity times 2 to the negative t divided by half-life. And let's work out what that right-hand side is. What's the initial quantity that we have in this problem? Yeah, 1 kilogram, so 1,000 grams. Is it 1 kilogram or 10 kilograms? It's just not up there. 1 kilogram. Okay. So yeah, 1,000 grams. So we'll try to do some color coding. So that's 1,000 grams. And I'm converting to grams because I see that the eventual quantity is in grams. So I mean, I'll have to work with a single unit at some point. Times 2 to the negative. Well, this is a how long will it take problem, so that means eventually I need to know what time is, so t will be the unknown. Divided by, what's the half-life? 70. And I'll even stick all the units in. 70 years. So that lambda is 70 years, not just 70. Yeah. And I think now I just have no choice but to zoom out just a little bit. Okay, and what's the eventual? We want to know when the quantity of U232 will hit some number. What is the eventual quantity we want? 1 gram. Oh, so there's an equation. 1 is equal to 1,000, well, 1 gram is equal to 1,000 grams times 2 to the negative t divided by 70 years. Nice. Well, that's an equation that we need to solve. What would you like to do to solve this equation? What's a good first step? Yeah, say it louder.
Divide by 2,000.
Divide by 1,000, right?
1,000.
1,000. So you want to divide by this. Because notice, this is definitely not the same thing as 1,000 times 2 then raised to a power. That would be different. That's right. Order of operation says you do exponentiation before multiplication. So we'll divide by the 1,000 grams. And I'm going to keep all the units in just to actually see them cancel. I know a lot of the times I don't. So 1 gram divided by 1,000 grams is equal to 2 to the negative t divided by 70 years. All right, let's see what simplification you see. What would you like to do to this? Well, I guess the grams cancel, right? Grams divided by grams is 1. Which is good, right? A power of 2 isn't something that has a unit. 2 to a power is just a number. It doesn't have a unit, so the left-hand side better not have a unit. Nice. So what would you like to do to that equation to solve that for t? What's a good next thing to do? Yeah, it's an equation in exponential form, and the exponent is the thing that looks complicated. So let's put it in log form. So, putting it in log form, the base is 2. So I'll see, I'm going to forget about the color coding. The color coding is gone now. Log base 2 of 1 over 1,000. And now it's important there are no units there. I don't know how to take the log base 2 of a kilogram. That doesn't make sense. It just has to be a number. Is equal to negative t divided by 70 years. And I've given myself not enough space to quite work this out in the detail I want, apparently. So I'll have to do something slightly different. Cool. What would you like to do next? Okay, you can say that. Multiply by 70. In fact, how about negative 70? Get rid of the negative sign too. And years, like you said. So I'll wind up with the log base 2 of 1 over 1,000 times, well, I'll put the negative sign out front. 70 is 70 years is equal to t. So it looks like we've solved the equation. Is anyone upset with that solution? Good. No one's upset because, well, of course you're not upset because that's not negative. Right? The amount of time that passes, it better be positive. But you all just already see that that's a positive number. Okay. Unless people like, because I mean it looks negative. There's a negative sign up front. But what can you tell me about the log base 2 of 1 over 1,000? It's going to be negative. In fact, log base 2 of 1 over 1,000 is the same thing as negative log base 2 of 1,000. So you could even rewrite this a little bit as negative negative log base 2 of 1,000 multiplied by 70 years equals t. And now the negatives literally cancel. And that's also a slightly simpler looking answer, right? I think that's as simplified as I can reasonably make it. I mean, maybe I know that like 1,000 is pretty close to 1,024, which is 2 to the 10th. So I know log base 2 of 1,000 should be like 9 point something. But if I wanted to do it more precisely, I'd have to use a computing machine, and I didn't bother turning the computer on when I got in here. So what is the log base 2 of 1,000 times 70? It should be the same as negative log base 2 of 1 over 1,000 times 70, right? What is this equal to? Is that about 700? So if you have a 1 kilogram sample of uranium-232 and you want it to decay down to 1 gram before you feel that it's safe, you're going to be waiting 700 years for that to happen. And so maybe that also like explains part of the problem of storing radioactive waste. If you have a significant quantity, you're going to be waiting a long time for it to decay to a small quantity. Let's do one more example involving radioactive decay. Let's talk about carbon dating. And maybe I'll ask this in fields like anthropology, archaeology, paleontology. You're interested in like old things like biology. And if you see like dead animal remains, you might want to know, well, how many thousands of years have these animal remains been dead? And one way to do that is a technique called carbon dating. And here's the basis. So C14, carbon-14, is a radioactive isotope of carbon. It has a half-life of about 5,500 years. The actual constants that I use, as per usual, are not as precise as they could or maybe should be. If you're interested in actually doing carbon dating, you should look up the actual half-life of carbon-14. In fact, many people are biologists or something else, and so they just know what the half-life of C14 is to more precision than that. What is the half-life of C14? It's pretty close to that. Okay. So if you want to know how long something's been dead, what you can do is you can find the remains of this animal. You can measure the amount of C14 in it right now. You can then say, well, while it was alive, the amount of C14 in this animal should have been about the amount of C14 in the atmosphere, which stays pretty much constant because the amount of C14 keeps on getting renewed by solar radiation. Wow. Well, cool. So that means that you have this radioactive substance. You dig it up, so you measure the amount of C14. You figure out what Q of now is. You know the initial quantity of C14. You know the half-life of C14. So you should be able to take this equation and solve it to figure out how long that animal's been dead, what T is. Let's do a single application of it. Let's suppose that you see an animal. It has died sometime in the past. You measure the amount of C14 in this animal, and you see that it has 4 grams of C14. Nope, when it died, it had 4 grams of C14 in it. You measure that it now has 10 milligrams, or nope, 1 milligram of C14. No, 1 centigram of C14 in it now. You want to know how long dead this thing is, how long this thing's been dead. So let's plug in the known values. How much C14 do we see in the animal now? 0.01 grams, but everything, the units are all consistent now, so 0.01, I'll just remember that it's in grams. What was the initial quantity of C14? So it's 4 times 2 to the negative, oop, there's a typo there, isn't there? That's negative t divided by half-life. That's also a poor place for me to have written that correction, because I need to use that space for log. 2 to the negative t, which I would like to know, divided by, what's the half-life of C14? It's 5500. Does that look like an equation that we can solve for t by doing something similar to what we just did? Let's do it. Let's talk through it. What's the first thing you would want to do to that equation to solve? Divide both sides by 4. So, dividing that by 4, I think that gives 0.0025 is equal to t to the negative, 2 to the negative t divided by 5500. All right, what would you like to do next? Yeah, but just say it louder.
Make it a log.
Yeah, put it in log form. So write it as log base 2 of 0.0025 is equal to negative t divided by 5500. What would you like to do next? Multiply by the thing you need to multiply by to get t on its own? Negative 5500, yeah. Maybe I'll interject. How many people at this point would be like tempted to replace log base 2 of 0.0025 with a decimal by using the machine? Okay, good, because that's slightly problematic. You should always try to prevent doing any of your rounding until the very end to avoid rounding errors from propagating. It's nice to get an exact answer at the very end and then approximate all at once. Okay, nice. So multiplied by negative 5500. Cool. So at this point, there's the same type of issue as before. Does that value for time look like it's negative? Is it really negative, though? No, because this thing inside of the log is something less than 1. So the log itself will be negative. Double negative becomes positive. And in the time that I've just stalled, what is 5500, negative 5500 times the log base 2 of 0.0025?
47,541. About.
5. I'm not a very good listener, so I picked up the 47,500. But the upshot is, I told you the half-life was somewhere around 5,500 years, so I'm probably really only confident of this answer up to that, because that's only approximately the half-life anyway. People feel pretty good? Cool. So there are some applications. There will be more applications tomorrow. Let's close by thinking about some just more interesting exponential equations that we can solve using these techniques. And this is one of the reasons that I hit record. The first section, I went maybe a little bit slower. And there was another homework question that people wanted to talk about, so I didn't actually make it to this sheet. So this will actually show up online. There will be 2 videos posted. Let's solve an equation. Here's an equation. 7 times 2 to the x is equal to pi times 30 to the power of x plus 1. Let's try to solve that equation. And at a glance, it looks really annoying to solve, right? I see an exponent on both sides, so I can't rewrite it in log form and hope that to be helpful. But I can apply a log to both sides. Let's see what happens if I do. What log would you like to apply to both sides? I say that it doesn't matter, but it kind of does. Which log do you want? Maybe I'll suggest either log base 2 or log base 3, because those are the bases of exponents I see. Can't use them both because you have to do the same thing to both sides. I don't know, log base 3. Let's apply log base 3 to both sides. Of 7 times 2 to the x is equal to the log base 3 of pi times 3 to the power x plus 1. And maybe I'll just convince myself that that's even a legal thing to do. Is 7 times 2 to the x definitely positive? Yeah, right? It's 7 is positive and every power of 2 is positive. And the same thing with pi times 3 to the power of x plus 1. And now let's use some log laws and see what happens. I see multiplication inside of that log base 2 of 3. What does log do to multiplication on the inside? It becomes addition on the outside. So I'll get log base 3 of 7 plus the log base 3 of 2 to the x is equal to the log base 3 of pi plus the log base 3 of 3 to the power x plus 1. And let's just look at each thing and see if we can simplify. Log base 3 of 7, does that simplify? Seven is not a power of 3 in any helpful way. So that doesn't simplify, but one thing I can see is this is just a number. There are no x's in it, so that's a constant. It looks illegible, but I wrote the word constant below. What about the log base 3 of 2 to the power x? Does that simplify at all? The x comes down to the front. So this next piece becomes, so that's log base 3 of 7, which is a constant, it's fine, plus x times the log base 3 of 2. Hey, the log base 3 of 2, that's another constant. So the left-hand side of this equation is linear. It's a constant plus x times a constant. The constants are funky looking, but that's okay. Let's look at the right-hand side. Does the log base 3 of pi simplify in any good way? No, but again, it's a constant, so that's not that bad. Log base 3 of pi. How does the log base 3 of 3 to the power x plus 1 simplify? It's just x plus 1, right? Because what power do you need to raise 3 to get 3 to the power x plus 1? X plus 1. Nice. So let's look at the right-hand side. Is that also linear? So this is a linear equation. We know how to solve linear equations. Get all the x's onto one side, get all the non-x's onto the other side, do some factoring on the side with the x's, and then divide. Would we rather put the x's on the left-hand side or the right-hand side? I think I heard left before I heard right. Well, it doesn't matter. So I'll subtract x to the other side. So I'll see x times the log base 3 of x, nope, log base 3 of 2, minus x is equal to log base 3 of pi plus 1 minus log base 3 of 7. Fair enough. And then let's see, the left-hand side you can factor to get x times log 3 of 2 minus 1. Yeah. Everyone with me so far? Yeah, and now you know what I'm going to do. I'm going to divide by that. So x is equal to log base 3 of pi minus 1, nope, plus 1, because it's plus 1, minus log base 3 of 7, all over log base 3 of 2 minus 1. People feel pretty good? Do you think if you used a different base for your logarithm, you would get a different looking answer? Yeah, if you use something log base 2, your answers would involve log base 2. But you know that log base 2 is really just kind of the same as log base 3, so that shouldn't be surprising. So again, this is a reminder, if you do a homework problem and someone else does a homework problem, you get answers that look different, but you have the same decimal approximation. Yeah. You can also do this problem with log base 10, and you would get a more complicated looking at it, but it's still fun. Anyone who still has to give me... Oh, I didn't collect these at all, did I? I did? Oh, okay, well. On your way out, hand with me. There were a few documents on the midphone.
I don't know what happened in mine. It's probably somewhere in my phone. And I didn't even
There was
touch
an email you sent. We don't have time to meet?
Yeah, on my phone.
Okay.
A lot of stuff. My sister was removing my phone and they called me.